Thank you, organizers. I hope you're not going to have a regret. This is not a bio talk, and this is it's entirely devoid of any biological context, other than the fact that I became biologically addicted to quantum models about 5 years ago. That's incurable, it seems, but here's what it is. So I'm going to talk about the model, which a way to think about it is the quantum spin glass model. Now, let me put you at ease. I know that majority of you probably are familiar with the classical spin glasses. That's kind of a baked in the workshop title. You're not perhaps familiar with quantum models. I'll just introduce enough of it so that we can be on the same page. So that's one kind of help that I commit to provide to you. But the other good thing is that even if you entirely miss this first kind of brief introduction to the quantum models, quantum spin glasses, still fine, because it turns out that for this specific model, it's not a universal statement, but for this specific model, there is an entirely classical, there is non-quantum counterpart to the question that we can make sense, and solving this question amounts to solving the question that we care about. So if you miss me on the first intro part, don't worry, there's going to be, help is on the way on the entirely classical, that is non-quantum reformulation of the problem. SYK and Sachdev-Ye-Kitaev model is a version of the quantum spin glass model, whatever it is. Before we get to the model, let me do this kind of a brief tutorial of how to think about quantum models, quantum optimization, how we think about Gibbs distribution, free energy, and things like that. Just enough so that we can be on the same page. Quantum optimization is really about, for quantum optimization, you have to consider the basic object is operators. So these are operators, linear operators that operate in 2 to the n dimensional space. So these are operators that linearly map these spaces to this space to itself. They have to be Hermitian. I'm not going to write it down. And so they have real eigenvalues. And optimization really means finding the largest eigenvalue for this operator. But of course, there is also a variational version of the same question, which is the maximizing a quadratic form. And I'm going to write it properly as quantum scientists would do. Like this. You maximize the quadratic form in this space over all vectors which have norm 1 with complex coefficient, right? So that part isn't just, in some sense, quantum science is a linear algebra on steroid, nothing more than that. If you're devoid of kind of physics part of it, from the computational mathematical part, it's just a linear algebra.
You don't need C-star algebra or something like that.
I don't even know what it is.
Okay.
I sort of know what's C-star algebra and so. But operator has to be Hermitian, so this has to be true. Okay. It will also help for the purposes of the example to think about one convenient basis in this space, 2 to the n dimensional space, which is commonly called computation basis. And it looks like this. It's very simple, but easy to confuse it with something else. So for all points, and I'm going to use plus minus 1 to the n as opposed to 0, 1 to the n. That will be more convenient that way. For each such bit string, you create a vector, which you also call it x, but with the bracket notation. So that's a vector in 2 to the n dimensional spaces. That looks like a bit string. If you have another vector, you can create another bit string. You can create another vector. However, the geometry in this space is entirely different from the canonical Hamming cube geometry. In particular, as long as x is not equal to y, these vectors are orthogonal. So you have one bit string, that's a vector x. You have another vector, That's vector y. Even if x is different from y from in one bit, this is an orthogonal vector. Unlike in the Hamming cube, which is not in where it's not the case. All right, so I cannot afford to go too deeply into more about that. As it turns out, even the classical spin glass model, which we remember what it is based on the operator summation Gaussians. So that part is entirely classical, nothing quantum about that. That should be familiar to majority of you, where x varies in a binary cube. Okay, you can rewrite this in the terms of the variational problem of finding the largest eigenvalue. But largest eigenvalue, not in a sphere, it's not a spherical spin glass model, largest eigenvalue in this space. The way you do that, you consider instead, you write this as a linear sum of operators, Z1, Zi, where the operator Zi, it's an operator, so it maps vectors, computation basis vectors to something else. So happens that it maps them computation basis vectors to other computation basis vectors up to the sign. And it's very simple. It is xi times x itself. Now, when I was learning this stuff and when I see something like this was just destroying my brain cells entirely. So until somebody really explains to you what is going on here is that this is a simple linear operator that maps a vector x into itself or opposite of itself, depending whether xi is +1 or -1. That's it. So if you think now, but this is an operator, so this is an operator that maps linear space to linear space. If you look at the largest eigenvalue of this operator, lo and behold, that's a ground state of the spin glass model that you understand here. So you can embed this problem in the quantum model. Now, for those of you familiar with quantum systems, not a surprise. It's just saying any classical model is a special case of the quantum model. All right, so that's going to be the end of a quick tutorial on what I needed to introduce.
What is this? These Z's or sigma Z's? How operators?
Always notation varies, but I'll piggyback on your comment. Z or sigma Z. That's absolutely right. But let me give you, maybe since you mentioned that, you're absolutely correct. There is another operator, which is now entirely quantum operator, which is sigma x, per Dennis's suggestion. This is an operator which is no longer diagonal in this basis. It moves x to a different operator, so to a different vector in the basis. And this new one is x prime, where x prime I is negative of xi and x prime j is xj. In other words, it moves one bit string representation of the vector to another one, which is entirely orthogonal to it. All right, time to express your pains. Right? Anything that I should clarify here, or yes, Marcus?
You now have to sum over like ordered tuples of the eyes.
Ordered tuples of the eyes. Right, and that points to the main difficulty in analyzing quantum systems, because once you induce here, pollute those with x and y's and z, these are operators, they don't necessarily commute. In fact, they don't commute, they anti-commute as it happens, and then the whole hell breaks loose. So what is the hell here that, oh, I have to see which one is correct. Oh, this one is correct. Okay, so hopefully you're with me. We can think about operators in quantum, in the space. We can think about random operators, because if I Just like in the classical case, if I generate those randomly, then I have a random operator. But that part is kind of fairly consistent with the classical model. We have a random quantum operator or random classical operator. Optimizing means finding the largest eigenvalue. So we can formulate the question, and we can do more than that. For example, what we can do is create an analog of the free energy, right? Both annealed and quenched. What do? From the operator H, you raise it to the exponent, you throw some temperature parameter beta, you take a trace. As it turns out, trace of this operator is just a partition function of this object that you're very familiar with. So it's not very difficult. It's really exercise to verify that that's the case. So trace is the right way to say partition function. That's the right terminology for it. So you take a trace. Of course, trace is random because the operator is random. It's a random variable. Now you can do two favorite things that spin-glass theorists do. Put expectation, take the log, and then take the expectation. One is quenched free energy, one is annealed free energy. So that part of the story, you normalize by temperature, that you don't have to do that, and fine. Now here's the headache.
David, so you didn't normalize by n or any. So like, should I think of those objects as being exponential in n, or like what is?
Good. As it turns out, I did not normalize by n. In fact, I will do it later. You can normalize by n. As it turns out that without normalizing by n, this is order n objects. Quantum classical, it's a simple exercise. I invite anybody to do that. That quantum spin glasses like this have a largest eigenvalue order n. After normalization, I didn't tell you what's the variance here, but that's that part. So some part of this is trivially extendable to quantum models. Some parts are not even barely extendable. So it's very kind of a dichotomical kind of situation. All right, so we have quenched and annealed. We know that computing quenched free energy is a major headache, right? That this is, you need a replica method, Parisi technique, whatnot. But this was done and so on. What about computing annealed free energy? Well, in classical models, computing annealed free energy is not even an exercise, right? This is just the answer. You can write it. It's a trivial thing to do because you exponentiate in classical model. You exponentiate e to the Gaussian, and then you have a formula for it.
If they're Gaussian random variables.
Yeah, if it's Rademacher, it's not. I mean, if you know explicitly the distribution is that, so it's right. It's fairly robust to the subject to the knowing the underlying disordered distribution.
No, because the annealed is a large deviation, so it depends on the distribution.
Computing annealed free energy for the spin glasses is easy, regardless for whatever is the distribution.
Unless the JJ are very correlated. And
Oh, no, I'm not saying that. In the independent case, of course, right? But I'm going to stick with the independent case. What about the quantum model? Here's the scandal. We can't compute. It's not easy. It's not clear how to compute annealed free energy for quantum model. It's just there's no good way to handle objects like this one. I should not be preferentially choosing one side of the audience versus the other. So this and this, right?
It doesn't work in any direction. Sometimes it does.
Well, if I can try to point to the audience, but
You make it pointed with two heads.
okay. Well, okay, yeah. Maybe use the chalk. All right, so that's kind of a general agenda that we're trying to pursue, even to get some tools, mathematical tools, to be able to analyze those questions. Now, for the SYK model, you're not going to like me for that, but SYK model is not a quantum spin glass model. It's something else, but not too different from it. And I will define what it is, but it will require some modification. We focused on the SYK model versus quantum. Quantum spin glasses are interesting, still very hard to analyze. SYK has been just so much in the attention in the recent years for several reasons that we felt we wanted to analyze that. So let me jump to the main result. The main result is that we've computed annealed, unquenched free energy for the so-called SYK model, whatever it is, provided the inverse temperature is small enough, in a high temperature regime, right? And
then annealed equal quenched.
annealed equal quenched, that's not our result, turns out to be the case for this model. So it's really a peculiar model for which annealed and quenched are the same for, I'll tell you
At
more.
high temperature. That's
Not at high temperature, at all temperatures. That's an interesting thing. So presumably, this should be a tractable problem, more tractable than classical spin glass, because annealed equals quenched. Don't you love that?
There's a minority of the community who doesn't agree with that statement,
Which statement?
that the annealed equals quenched at all temperatures. For
No, that's a theorem.
It's a theorem, really. Where?
Yeah.
For SYK.
For SYK.
SYK, it's a
theorem.
theorem. Yeah, it's
Annealed
not.
equals quenched.
Yes, no space for disagreement.
Really?
Yes,
Okay.
I'll give you the reference. Yes. Yeah. So this is the cultural advantage of being in mathematics. We don't make it, but once we prove something, we're fairly convinced that.
No. I'm just surprised.
Yeah. Maybe you're thinking of a different variant of the model. Let's be careful about the details, and I'm sure there's.
Write down the model so at least we know what's being discussed.
I will. Okay. All right. All right. And there's reasons to be interested in this model because it has some fascinating connection with the black hole theory and then the holographic duality and so on. I don't know anything about that. It's really not interesting, fascinating stuff, but I can't comment on that. But for whatever reason, that it's an interesting model. So here's the model. Here, part of it is just the canonical spin glass part. You sum over Gaussians. Gaussians are IID, standard normal. There's some normalization here, which is convenience, some extra factorial. Don't worry about that. Q is P in your typical spin glass notation. So instead of P, we use Q because that's a standard. So you have Gaussians. And then what you do, you take the product of operators. As it turns out, interestingly, all you need to know about these operators happen to be called Majorana operators is that they square to half identity and they anti-commute. So for each I going from 1 to n, just like in this space, on this space, for each I, there is an operator, Majorana operator, and it has to square for convenience. It's a half identity operator, and it's anti-commute in a different location. As it turns out, for the purposes of computing ground state, free energy, quenched or annealed, that's all you need to know about that. But this is still too implicit in terms of what it is. You want to get perhaps a more explicit way of writing it down. There is an explicit way to write it down. I'll do that.
David, so this operator is not clearly self-adjoint, right? We're not going to talk about. Is it self-adjoint?
It is because of the I.
Oh, okay.
Yeah. But in fact, interesting cases where Q is even, and in that case, I squared is either I to the Q is over 2 is either 1 or -1. So it needs to be self-adjoint, right? So what are the Majorana at location I? It turns out that equivalently, you can write it like this. You take a tensor product of Z Pauli operators up to location I -1, and then you take either X or Y Pauli operators, and then rest is identity. Depending if I is even or I is odd. So it sort of has this flavor or XYZ flavor, except for it's not local anymore. You have to take a product of Z's from the beginning up to the I. All right, so you didn't quite get that. That's no worries. As I promised to you to give a classical reformulation of what we care about anyway, but that's exactly the model that we will analyze. Physics literature on this model is huge. Physicists more or less computed everything they wanted to compute about this model. In particular, Maldacena and Stanford computed the free energy and lots more ground state and lots more other things using physics method, which is in fact a combination of a replica method, but also a path integration method that's much older method in physics and quantum physics and so on. All non-rigorous. That's not clear if it's rigorizable or not. That's a separate project. Right. Now to the mathematical literature. Part of it is that's quenched equal to annealed. So much more limited. Math literature is much more limited, but there is one. So we know the ground state is order n. That's not very hard to show. Lower bound was more harder to show. And the important thing, and apropos the earlier question, is that we do know that the quenched equal annealed in this model asymptotically. So you take expectation outside or inside, you get the same answer. Quick one-line reason for that is it turns out that variance of every state. So in other words, variance of the energy of every state. So you take this quantum state, you evaluate it with this Hamiltonian, you look, that's energy, it's a random energy. If you look at the variance, it doesn't scale like n in classical spin glasses, it scales like 1 over n to some power. So it's much smaller variance. Because of that, the concentration is far stronger for the entropy versus energy to be in competition. So energy wins. That's kind of a one-line reason for that. But it's very non-trivial, really nice result. Quenched equals to annealed. But the method doesn't tell you what it is, right? It just tells you two things are the same. Yes, please.
Sorry, this result holds also for temperatures that are like 1 over n to something, or it's...
No, it holds for constant temperatures.
Order 1.
Order 1, which are the right temperature to consider to map to the ground states, and same scale as the classical spin glasses, right? But for all temperature, there's no phase transition. Good. All right. So after hours, the list of rigorous works in this area has continued after we posted our paper. So one paper actually computed free energy for all temperatures. It's a paper by He. The paper is ChatGPT produced. We used the assistance of ChatGPT as well, but at least we make an effort to make it human readable. That paper is really hard to read, but it seems correct. So Chat thinks it's correct paper. So it's a legit and so on. But understand the idea and logic and intuition. It's very hard, but it's to be done. Seems correct. The other paper did something else. These authors proved that as Q becomes large, the ground state scales like this, and this is consistent with the physics prediction.
It's the.
Q is the parameter. Q is P.
It's the order of this. Okay.
Yeah. This was predicted in physics, and those folks proved that rigorously. And this is a very nice paper with all intuition and also ChatGPT. I mean, that's the time we live, right? So, but it's very nice, kind of readable. You understand what is going on.
In writing it or reading it?
So
So which way around is it? ChatGPT helped in writing it or in reading it?
both. So you asking about that paper?
Yeah.
So they don't say on what part specifically they use ChatGPT, the proof construction as well, but they made a very good effort, commendable effort, I would say, to write a paper so that others can read it and understand what's going on. Which part of it is their own creativity, which part of it ChatGPT or both?
Okay.
That
Humans can read it.
humans can read it. That's the kind of
And these calculations are done on the annealed or the quenched or their.
their calculation is for the annealed.
Okay. And then you use the theorem to say.
Yes, good. Yeah, I think so. Yeah, good. All right, so let's get to what we wanted to report. As I said, so the quenched equals to annealed. That much we knew already. The question is, what is the limit? And that's what we compute for small enough constant temperature. Technical reasons, it's even Q, but that's the case which is of interest in physics. So we compute this limit And incidentally, it was not even clear that this limit exists. Well, prior, now we know it exists, but a priori you wouldn't even know mathematically rigorously why such limit exists. If you recall the classical spin glass development, the existence of the quenched free energy limit for the classical spin glass by itself was a non-trivial observation of Guerra and Toninelli using Gaussian comparison method and so on. So because a priori you wouldn't even know that such limit exists, but it does. Physicists would never argue about that. Of course, the limit exists. Why would it be periodic in n? It doesn't make sense. Good. So now I'm going to introduce the same question in a technical level.
Only for Q, P even?
Huh?
The theorem is only for P or Q even?
Yes. Yeah.
There a good reason for that? Or
So it's to do with the symmetry, in that case, the symmetry of X to minus X things? Or?
well, there is no. I'm trying to remember if so where. I think if Q is not even this scale changes. I think it starts acting a little strangely. This is a strange model, but good. So now let me introduce restate the same question of computing annealed free energy, but in a classically friendlier way, in a way that does not need to appeal to any quantumness. And that's the second thing that I promised to you, and now I'm gonna fulfill this promise. It turns out, for this specific question, yes.
Voilà. Before we go to without quantum, if we say 2 minutes on quantum,
Sure.
Is there a notion, so that you have the free energy, but is there a notion of Gibbs measure or something?
Yes.
Structure of
Yes.
the low states or
Yes.
whatever?
There is, and it's odd. In a way, it's odd. What you do is the analog of the Gibbs distribution and Gibbs measure and things like that is what is called the thermal state. What is the thermal state? It's e to the beta h without any expectation. So it's an operator itself. So that operator itself is right analog of the Gibbs distribution. Why? Because if you look at the eigenspectral decomposition of this operator in eigenvalue and eigenvectors, in a classical case, you would recover the Gibbs distribution. Eigenvalues will give this probability values, and eigenvectors are trivial in a classical sense. So thermal state is the right object in the quantum system, which is e to the beta h.
Is it understood?
No. It depends on the model, of course, but SYK, it's really bizarre. For example, it is believed that at the edge of the spectrum, the distribution of eigenvalues behaves like a semicircle law, which is nothing like classical spin glasses, where the number of eigenvalues above certain energy sort of decays exponentially, right? It becomes very kind of a tailed behavior. For SYK, it's believed that it's not like that. It has a density all the way up to the ground state.
Is there a notion of overlap of replica?
There is a notion of overlap of replica. You can do that with the X and YZ operators, but you can introduce the notion. We don't know much about it. Really? No, you're asking exactly the questions that we were asking. Like, what can we say about that other than nothing? Right. Good. So somewhat back to classical models. Turns out that technically what you have to do is solve the following proxy problem, which can be conveniently formulated in terms of the Erdős-Rényi hypergraphs. So that's a model convenient for us. Others might use some other terminology here, but for us it works. So let me remind you what the Erdős-Rényi hypergraph is. You have n nodes. You generate R hyperedges uniformly at random, and hyperedges all have size q, which means the hyperedges are just subsets of cardinality q. When q is equal to 2, that would be edges, the pairs of nodes. But we need to look at the q, general q, so that would be a hyperedge. So subsets, good. So let me prepare I can. So this is a superset of nodes, and you throw some Q size subsets. Some of them are intersect, so all of them have size Q. Good. Then we need to do the following extra randomness.
In the limit, each site is in many of these clusters or order one, order one.
It depends on the ratio of R to N. Turns out that the relevant ratio is when R is of order N. In that case, the number of the degree of the node, the number of hyperedges containing the same node has a Poisson distribution in the limit. And that's the right regime to look at, as it turns out, mathematically. Okay, but we need to do some other source of randomness. What we do is that for each hyperedge, we generate a random uniform chord. A random uniform chord is just two random independent points on a unit interval. Okay, so I have a picture a little later on, but let me continue in here. And then for every two hyperedges, E and F, we introduce a ±1 crossing function, which looks like this. If E and F don't intersect, the value of the function is 1. Just that's a typical situation. So if these two hyperedges don't intersect, the value is 1. If they intersect at the odd number of vertices, which, by the way, is a typical situation, typically in this random graph, if they intersect, there's only one common node. So if they intersect in one node, then we put -1 when these two chords cross. What does it mean to two nodes cross? So let me jump to this. So here you have one chord, you have another chord. If they look like this, they cross. If they're nested, or if they're disjoint, they do not cross. So this is the crossing situation. This is non-crossing situation.
I'm confused. What is this axis and how?
Axis here, this is an interval from 0 to 1. Let me also draw it. This is the interval from 0 to 1. You throw a chord, so it's just a random 2 points. That's the first chord. You throw another chord. Let's say it's like this.
You throw a chord for each pair of vertices.
No, sorry, it's a little confusing. So each of these will have its own chord generated. Like this. So each of these, now think of it as the kind of a label for the chord, but each of these hyperedges will have its own chord. And then what you do, you're saying, okay, for these two, they don't cross, they don't intersect, so I don't care about this. These two hyperedges intersect in one location, which is odd. And now I look at the chords, this chord and this chord. If these two chords are like this, they don't cross, value is 1. If on the other hand, they're like this, it's -1. So it counts both those pairs which are intersecting and those for which the chords are crossing. Then it's -1. Otherwise, it's 1. Okay, so why that? Oops. Then what you can rewrite, as it turns out, the free energy, anneal free energy, as follows. There's some common part, which is, well, temperature. That's not an interesting part. The key part is here. You need to take expectation with respect to randomness of the graph and the randomness of these crossings. So these chords, right? So there's two sources of randomness. And take the expectation of these products of 1 and -1. Basically see the parity of this crossing diagram. So how often it is 1 versus -1. If you solve this problem, you solve the free energy annealed quenched. That's it. Yes.
R is monolistic.
R
Is them independently such that the expected number of hyperedges is R.
No, R is here, so you can think of it deterministic, but then you sum over all values of R's in here. So this is R appears in here. And so you need to look at this question about across all random graphs edge numbers. So R will go from 0 to infinity. As it turns out, the relevant R is when R is linear in N. Yes.
So, isn't I right if I try to understand this as if I do the physicist thing of doing the path integral with Matsubara time from 0 to 1? Is this a representation of the path integral? Because so this interval 0, 1 looks like some time and then you.
I understand this question, or rather, I do not understand this question, but because it's only because of the lack of my background. So some physicists said that, in fact, for what it's worth, there is a connection between this diagram and this and what is called the melonic structures, which is how physicists think when they implement the path integration method. So it shouldn't be a coincidence. It should be this, but beyond that, it's hard for me to make this thing mathematically precise. All right. So, but now, okay. So it is what it is with whatever connection. So if we understand this expectation, then we're in business. This is really like a large deviation question, because now you're thinking with respect to the random graph, how often this product of signs is 1 versus -1. Right? So it's not going to be behaved by the typical realization of random graphs. It's going to be atypical. So some large deviation thing will kick in.
Sorry, the plus or minus 1 is just because they're fermions. Yes?
Plus or -1 is because these Majorana operators are anti-commuting. So I'll be careful because I don't even know what's a fermion. You know, I don't. Okay. So because they are anti-chem, yeah. So and this diagram, the crossing diagrams has been in the literature in physics and even this math and literature for a while. It's been appreciated that this is the key to understanding anti-commutation, and that, guess what you would suggest. Okay. Now let me give you the answer. What's the free energy? I'm gonna begin with the extremely unfriendly version of the answer, so that you just see what mathematics of the answer looks like, but there's no intuition behind it. And then I will give the friendlier answer. So first, unfriendly answer. As it turns out, you need to solve a certain fixed point equation in a function of two variables, z and x. Just to help you a little bit, think about solving a version of the branching process, how do we understand the branching processes, right? We can use the generating function, write down fixed point equation, and it will tell us what it is. This is sort of what it is, except for you have the sine function thrown in. So some function fixed point. This fixed point exists, provided in some region, in a complex region. From this function h, you construct another function, r, and another function, e. The h doesn't have much explanation, intuition, so r and e are completely perhaps unclear, but technically this is what you arrive at after doing mathematics. And now to get to the final answer, what you need to do is the following. Rho is a reparameterized beta. Beta is the inverse temperature, so rho, you reparameterize it for convenience, so this is not a big deal. Then you combine these two functions in some reparameterized way. You get another function f, and then you solve a certain kind of large deviation type question, which gives you the following fixed point equation. You need to find a solution such that the derivative of this function times t star is 1. It's all mathematics. It's all, rigorous, of course, needs to be done. You arrive at something like this. Once you find this value t star, the free energy is given by this equation. Free energy at high enough temperature beta gives you this equation. All right, so it's kind of mathematics without much kind of a story to explain.
So
But I'll give you a parallel.
F depends and T star depend on beta as well.
F does not depend on beta. F is a function of R and E, except for the R.
Rho depends on beta. Okay.
Yes, yeah. But here you think of F as a function, right? So it's no, you're right. F is parameterized by beta. You're absolutely.
So T star.
Okay. All right. So that's the answer. But I'll give a friendlier version of the answer in a couple of minutes, and then I'll wrap up. All right. So we computed free energy, but the physicists computed free energy. It better be the case that our answers coincide. They do. So I'll show you the pneumatics, and I will show also the answer that was produced by physics using path integration and the replica method. It also involves fixed point equation, but it's a different kind, and connection between the two is to be resolved. It's not clear. So our proof method is mathematical. It's not based on path integration and replica. It is based on familiar for us things, component structure of sparse random graphs and the cavity method. So putting these two things together, that will it derives this result. So let me go over this. This part, the component structure of random graphs, is probably something familiar to lots of you. It's just the theory of Erdős-Renyi graph and phase transition, things like that. Let me remind you what it is. Basically, it says that in the random graphs, there is a phase transition of the following kind. On n nodes, if you throw linearly many edges, depending on the density of number of edges to the number of nodes, you have two situations. If the density is less than 1/2, this is for non-hypergraph. This is for just graphs. Then all connected components of these graphs are small, order 1, typically order 1, and largest one is order log n. If you cross the phase transition point, then the giant component emerges, which is linear in n size. So let me show you the picture. This is all the textbook knowledge of Erdős-Renyi theory. So no big components. All components are order 1, most order 1, and in fact they're mostly trees. Once you cross, then you have a giant component which is large. As it turns out, for small enough beta, that technically corresponds to the pre-giant component phase. So components, whatever that means, where is that component? That to be explained. But most of the tip components in action are small. There's no phase transition. There are trees, and that allows you to do certain branching theory type computation, fixed point equation that you need to do. So and to do the branching theory version of it, we use the cavity method. The cavity method is a physics method, but rigorizable, often the case, apparently, in this case too. What you look at the ratio of partition functions, original and one node removed. And there is this ratio tells you it's what's called the cavity. The idea is that you can analyze this cavity in terms of the nearby cavities of neighbors, because that gives you certain propagation equation, commonly called belief propagation equation. It's just the terminology. The point is that this is the right object to look at if you want to understand the marginals of your systems. So when you do that, long story short, this is what you found. Now, in this slide, this is probably going to be my second. I have 2 slides left, so keep me control.
So you have the same kind of percolation picture for the hypergraphs that you need to do here.
Yeah,
it's the usual Erdős-Renyi, but
yes,
you need a more complicated version.
Effectively, we use the fact that if the temperature is large enough, beta is small enough, then all the action is in the case where the components are isolated and tree-like in a hypergraph.
In a hypergraph.
In a hypergraph. It's a
Typical beta beyond which there's an infinite component. Is that?
There is a certain beta which we don't know how to compute, beyond which it certainly breaks, and then you would have to use some different techniques to compute free energy. That's a work in progress. But yes, for large beta, it would not be dominated by small components for sure.
Your results are only for small beta.
Yes, that's the reason.
So for large beta, you would have this big component somewhere, but still anneal would be quenched.
The anneal is quenched.
Wow.
That's a theorem. Yeah.
Wow.
Wow. There's a after lecture I can give you some ideas why that's the case. There's a certain correlation decay happening in the cavity structure, which probably explains. But I need to start wrapping up. All I wanted to say is that there is a way to rewrite a function f which drives the free energy in a more combinatorially understandable way. So what is the way? And this is how we arrived at the formula originally. What you do is that for every value of v, which marks the cardinality of a tree size, you sum the following object. You go through over all trees of the cardinality v, and you look at the expected crossing numbers for these trees alone. For when you have a tree and you want to compute the expectation of this product of the crossings, this is a friendlier object. You can compute it by the cavity iteration. It's much nicer. It's order one object. You can mathematically do that, or at least you can do that numerically. What we did. So this is what you compute for all three sizes. And then you create some kind of like a generating function. No, this is not the generating function yet. It's just a v-dependent quantity. And then f is a generating function of such three counting object. As it turns out, and from that, this is how you prove that. All right, so now just to wrap up, I guess let me show just one slide. Physics calculation that arrived at the same, we arrived at the same calculation that physics. There's two curves here that are matching, so numerically it's agreement. Physics answer is given completely differently. It's in terms of a fixed point equation in some transform domain. And the answer works for all temperatures. There's no limit. There's no phase transition in temperatures. Now that's another evidence that this quenched this.
Sorry, there isn't a transition.
Huh?
There isn't a transition in temperature.
Where in SYK?
Yeah.
Which one? No, not in quenched and anneal. Quenched and anneal are the same across all temperatures.
Behavior changes in the thermodynamics is smooth, but that you do get an infinite cluster. So there is a transition.
I'm not sure.
Energy is
No,
smooth.
even at the physics level, but I might be missing missing something. Certainly, quenched and anneal. Okay, it's not sort of to be sorted out. So there is a fixed point equation that you need to write in transform domain that also gives you the answer for the annealed energy. Numerically, two things agree. Mathematically, why do they agree? Even at a high temperature, we don't know. That's an open question.
Here you have some kind of functional parameter. It's a function between 0 and 1. In this physics derivation, do you have a function in your formulation just to try to make some contact?
Which is
I mean, here you see that this sigma and g. I mean, you discretize, you go to
and there is
a function.
It's a function, and this function, as you said earlier, that comes from the path integration, right? So you do the path integration over some time, whatever you call, and that gives you this. No, we don't have. There's no time analog of this. We're not using path integration.
In
It's
gravity method. There is no function that you
no time.
It's a fixed point.
No time. No, nothing natural. So even at the conceptual level, it's a little difficult. But there should be connection. I don't believe in two theories giving the same answer. It should be one answer. Yeah. Good. I have some open questions, but you can read offline. I'm gonna leave it at that. Thank you.
Is there a combinatorial reason? Like, is the exponential moment easier to understand than the trace of a fixed kth moment?
Not sure I followed. Say it.
So for instance, you're computing the expected value of trace of e to the beta h by some diagrammatical expansion type thing. Can you do the same thing for the trace of h to the k for fixed k?
Oh, it turns out that we end up doing exactly that, except for k has to be order n.
Yeah, I guess my point is if you do this for each fixed k, you would prove the empirical spectral moment is converging to some deterministic quantity. And then maybe if you prove tightness, then you get that the biggest eigenvalue converges as well in the ball.
Well, but true, but that's where the difficulty is that you have a object which is, well, it's an n-qubit system, and you need to take it to the power order n. Eigenvalue itself is order n, so you need to take it. You need to take a power order n, and it's not clear how to analyze even the expectation of this trace of this operator. You would think that it should be elementary. H to the n, h to the k expectation. How difficult is that?
So your fixed point equation has unique solutions for small beta. That's what you need in the proof.
Yeah, that's right.
So the formula that you proved, presumably it's analytic in beta, so it should be the formula for every beta.
Yes, and there was wrong. So were formula. Yeah, f of z. I mean, there's another version of it. Yes, so we were even thinking that maybe we can just prove that this whole thing is analytic and therefore extends to all beta. But it has to be analytic sufficiently in a limit uniformly in n.
Yeah.
And we don't know.
So the formula that was known in the afterwards paper is not the same as this for all beta?
Good. So the one, this paper, which is difficult to read, but seems rigorous, I think it rederives those answers. It basically hacks it out, the derivation, so that this actually makes sense. But there is no path integration in argument. It's the paper is actually the only part which I understood from this paper is that it uses the interpolation method, the same that Talleyrand and others used to justify Parisi's formula, except for it's really complicated and so on. Somehow, then it's hacked to produce the same answer.
Sort of, I mean, this looks like a very cavity thing that always comes in exactly this form. So it must be some combination of doing cavity and then thinking of the Feynman diagram.
Right. As it turns out, what you interpolate to is fairly complicated. It's decomposable system where you have, for each qubit you have its own Majorana, several Majoranas, but it's still parameters are being adjusted to some complicated way so that the interpolation argument works. Maybe this is not the
argument, self-consistent argument for it.
Maybe I want to make sure I understand the question before it.
This is coming from a cavity.
Which one? This? So this is path integration.
It's cavity and path integral. I mean, to get this.
There's no.
Yeah. You do the path integral, you use Matsubara time. You do it's like just dynamics, real dynamics, but just on imaginary time.
Yeah.
And then you get Sachdev contribution. These are the Sachdev contributions. So
Okay,
you can
you
think
use
about
logic.
path
Yeah,
integral
it's the
like,
same, yeah.
it's a-
Good. I'm happy that you have it, but I don't. But okay, that's to make sense. We were trying to rigorize the path integration, and that runs into mathematical questions. Of course, it gives the right answer, but what's the mathematics?
Of course. I mean, there's lots of fancy calculations of physics that give wrong answers. Actually.
Okay.
Okay, thank you.